My name is Mark Notcutt, and I'm from Stable Laser Systems, and we're a 15-person, 12-year-old company in Boulder, Colorado. We sell complete frequency stabilized systems, such as clock lasers at the so with Allen deviations in the 10 to minus 16s and 10 to minus 15s. General spectroscopy lasers for cooling and atom manipulation. 1550 nanometer stabilized lasers at the Hertz level for general metrology, and these have very long lock times in non-lab environments, such as some shacks. We also sell just Fabry-Puro cavities with custom coatings that you can use as reference cavities or for spectroscopy. I'm not sure if you can see the beautiful multi-bore cavity on the bottom right, and that you can use to stabilize just a bunch of lasers. And then lastly, filter cavities, which you would use to filter laser noise or filter frequency combs. Okay, so the picture on the left here shows a complete clock laser system. And I guess, let me just apologize right away that it's not in a sort of a 40 centimeter by 40 centimeter box with nice heat sinks all over it. But anyway, this system is a 1542 nanometer laser, distribution laser, which is stabilized at the Hertz level, and then a clock laser, which is has the same frequency stability, and that is transferred through a frequency comb, and the clock laser has fiber noise cancellation so that it can be delivered to the, you know what I mean, the physics cell. Also, there is a 10 and 100 megahertz RF outputs from the comb, divided down from the comb with one of Franklin Ascarance's dividers. So all our hardware is generally based on FPGA, you know, control, and this enables you know, great features that not just you know, very low offset locking, but it means that you have wonderful remote control capabilities, wonderful, you know, on-the-fly setting of parameters, and also it is sending back, it's pushing data back to the user so that they can monitor the system health. You know, they can see when actuators are going close to the rail, if some temperature, you know, it's in the lab is getting too high. So, you know, it's kind of a step towards a very independent system. I just want to say that in this case, we do a lot of offset locks, and in this case, the clock laser can be moved around in frequency, you know, through the programming a DDS word, and this allows you to the user to program the frequency steps that you need to drive a clock transition to generate an error signal. Okay, and then look, I just showed you a little square wave on the right there, 200 hertz, but you can do many different things with the command set. Okay, and then next, so for fiber noise cancellation systems, you know, this is commonly used in laboratories. So Stable Laser System sells both complete systems, or you can just buy the control electronics. And you know, if you lab user, you may just want to control electronics, and then you can set up your own interferometer or move it from, you know, one experiment to another as you need to in time. So this idea was developed at NIST and JILA, and it is essentially a phase stabilized Michelson interferometer with the AOM providing the feedback. The feedback is of course in frequency, but nonetheless this allows the remote delivery of stable frequency to a reflector somewhere in your system. You can also use this box just as a digital phase lock box, and it, you know, has all these sort of flexible menu options. You can drive AOMs of different frequencies. You can set all the PI parameters. You can set the output power. You get status output. You get remote control, and also because there's an AOM in the system, if you provide a photo detector signal, you also get a optical power control. And in the graph there, you know, I'm not exactly sure what's limiting that. It's probably the reference arm of the interferometer, but you can see it starts at 10 to the minus 16 and works its way downwards in Allen deviation. So if you need to travel much further than one fiber link, and that's a slightly more complex discussion, but you can set up a repeater station to regenerate a very narrow wave for onward transmission. And the way to do this, or one way you can do this, is with a stable laser system's 1 Hertz offset locked stabilized laser. So the laser is not directly stabilized itself on the cavity transmission. It's sort of, you can set the operational frequency through a DDS word, and this means that you can regenerate the incoming light. The incoming light may be degraded in its optical spectrum because of the phase noise imparted by the previous fiber link. And so you may just want to lock your regeneration laser with a few Hertz, phase lock loop. And this is ideally suited to the digital electronics that's in this box. So you can, accurately regenerate the source phase and frequency for onward transmission. Okay, and again, you have full remote control. You can have this unit out in a shack, and you can sit at your desk sipping tea. All right, and so I'm just going to summarize there and saying we sell a lot of great hardware that you can use to form flexible solutions for your timing distribution needs. And with SLS, it's just hurt so good. All right, thank you.